this term squared. Because they are from orthonormal basis. And this equation here was using this fact. So now you look at the definition of theta 2, which was that it's the dual basis of E1, but E1 was like scaled by dx, so that means in this case this term actually vanishes because dx is proportional to E1, and theta 2 vanishes on. And similar here we get actually the proportional factor, which I think I wrote it down at some point, was that this one here gives you the square root of GG1 by the definition of what it means to be E1. That was the 1 over the square root of GG1. So that means if you take the square root of GG1, what you get if you square it, of course, is G11. And that shows you that if you take the pullback of the first fundamental form in x direction, you get G1 back. And now you do a very similar calculation for the other factors. Yeah. I don't think I use the example anymore. So. Shows that the pullback of the whole first fundamental form is given by this matrix G. Okay, so that's the first thing that we had to verify. And we also have to verify that the pullback of the second fundamental form gives us L back. So the calculation is similar, but not quite the same. So let's do it again as an example in the dx direction. So the first step is okay. We need to verify. We use the definition of the pullback. So we get here psi dx psi dx. And then as we did over here, where we also said like, okay, the psi dx is something in terms of E1 and E2, and then you get the thetas in there. So in this case, it boils down to the following thing, that we can simplify this expression over there to having the square root of 1, same xy direction, E1, and the other factors, they don't contribute. So now we use the definition of the second fundamental form. So that gives us an inner product two terms give us the inner product of GG1, and then we use the definition that it's E1 times the inner product of the shape operator at the point psi x and y in the E1 direction. But the shape operator was given in terms of the derivative of the third vector in the E1 direction. So now we can, like the only thing that we need to know, namely, can use this equation over there to rewrite this expression here as minus the sum over all i's of omega, sum over all j's in the xy direction E1 Ej. So it's a little bit of a piece of notation, because here E1 is really a frame on S, but here it's these vectors that we constructed at the beginning. And okay, so we insert that, and the sum actually simplifies, and what we end up with is that only the third term contributes. So it's omega 1, 3 at the point x and y in the E1 direction. So now we use the definition of omega 1, 3 that we had in terms of L. So we get it's G11, and then we have a lovely double sum here over Lij, x and y, dx by E1 dxj E1. And now we use that. Here we use that E1 was defined as 1 over the square root of GG1 dx. It was the normalized version of dx with the respect to the g. So that means that if you insert this expression in here, what you get is that E1 is like picking out the first elements only, and in each element you get one of these factors of the square root of G11. So that means the square root cancels this factor, and what you end up with is that the only surviving term is L1 by dxy. And then, again, similar calculation. Shows that the pullback of the whole second fundamental form gives you this matrix L that we started with. And that leaves us in total with the following theorem, which is the fundamental theorem for surfaces, which has two parts. Namely, the first one is that if G and L are families of symmetric matrices, we want Gij or G to be positive definite, and both of them have to satisfy the Gauss-Codazzi equations. Then there exists a parametrized surface S such that G and L are the local parametrization or the local representations of the first and the second fundamental form of S. So that's the first part, is that if you give me G and L that satisfy these properties that they are symmetric, that's like clear because the first and the second fundamental form are symmetric, and G is positive definite. That's because it has to be an inner product. So these ones are like very natural conditions. And then the important question here is that they have to satisfy the Gauss-Codazzi equations. And if that's the case, then we can reconstruct the surface, at least locally, with its parameterization, given like G and L, such that the local representation of the first and the second fundamental form are exactly the matrices that we started with. So that's the first part of the fundamental theorem for surfaces. And the second one says that locally a surface is uniquely up to a translational and rotational, like a global translation or a global rotation determined by the first and the second fundamental form. So once you know the first and the second fundamental form of the surface, you have complete information about the surface locally. So you know everything about the surface locally. Of course, you don't know how it globally looks like far, but like at least locally, you have complete information given the first and the second fundamental form. And this theorem, in some ways, gives you a justification why it's called first and second fundamental form, because that's the information that I have to give you in order to reconstruct the surface locally. So that's the result. What I want you to remember is this theorem So the statement of the theorem you should know. The proof is like what I discussed before, is like you should not know for the exam, it's not relevant. But I think it's good to remember that the strategy was that you construct of G and L, you construct the dual forms and the connection forms, and then once you have the connection forms, you can integrate that by the structure equations. So again, these structure equations are like so important because they kind of like tie the local geometry of the first and the second fundamental form to the parameterization. So that's what I want you to remember from this first part of the lecture. And I think that's enough for the first part, so let's continue in 15 minutes at 20. Yeah, let's say 20. That's the definition. Like you, yeah. So like that was like one of the parts is that you define out of G, you define E1 and E2, and then theta 1 and theta 2, and then omega 1, 2. That's like defined in terms of G, and omega 1, 3 is defined in terms of L by this formula. So it's like, I had that like, I think it was somewhere, like it's really like just, once you give me L, I have to do something with the L, right? And the idea was that, yeah, okay. As to omega 1, 3 is the sum of ij, ilj, and then dxi. I think somewhere to insert or some. I think maybe some. There should be. Yes, thanks. And this one should be V3 then, right? Or one of them should be V. Yeah, like I think you get it, right? Like.
I don't understand why you should define that.
That comes from the structure equations. Like assume that you have a local parameterization. Then you pull back the structure equations of like that you have with omega 1, 3 in terms of the second fundamental form, and then you write this as L. What you end up with is this equation. That's the structure equation that you get. So maybe so what you have is like you have S, then from that you have the first and the second fundamental form, and you have omega ij here. And then you have psi, which goes to D, from D into S. So you pull back this information, what you get is G, L, and yeah, maybe now I use like a different notation. And here you have like the structure equation, they satisfy. So if you pull back, then these ones also had to satisfy the structure equations. And if you write them, then you end up with exactly these formulas. So, and the idea is now to do it oppositely, that if you have this information here, then you construct the omega ij's using this formula. Because that part you have not yet constructed, right? Like if I give you G and L, you have to. The idea is to construct this guy, and then from this information you construct this, such that if you then pull back these data, you get like the original data back.
This means the structure equation.
Yes, exactly. Yes. Yes.
Why not omega 1, 3?
Okay. Yeah, I have to agree because it's like yeah, maybe. Okay. I agree that would be also natural. What do you mean? Oh. So
Is that right? Because we know we define E1, we have already defined E1 as we know that.
yes, so you could. I don't know how they are related.
I'm trying to now use your formula and compare it to what I have. Omega 1. That was this one homework, right? That I did to, that I couldn't look at other permutations for tests, and that was like possibility. So I think that is plus minus x times k is L11. Might be a figure 1 and figure 2, and they're also relatively complicated. If you write in a work form again, in terms of figure 1 and figure 2, you might end up with calculus. But it's a good idea. Next time I'll show you. So you said that's confusing. What is confusing about the notation?
In the homework, in problem 2, you need to use the equation problem 3. But when I calculate this, we found that we can't use this to get this.
Okay.
And we find the mistake in our calculation.
Okay. Cool. Okay, I will try to do it this evening instead. Maybe I did some mistake, like some dots or maybe one or something. It should really be just that you use these equations for this particular setting and then just derive these equations. So if not, then I did maybe something wrong, and then I will have a look. But thanks for letting me know. Okay, let's continue. So the last like hour or so today is a bit of preparation for next time. And next time the idea is to go from local information to more global versions. So what we have seen now in the statement of the fundamental theorem is that locally everything that you need to know about the surface is the first and the second fundamental form. Then you know the surface locally. So the question becomes now, okay, we understand it locally. What about more the global thing? Like, for example, if I give you a certain shape, how many holes are in that shape? Like, you know, like a donut has one hole, the sphere has no holes. Maybe you have like some surface that it has a bit more holes. How do you recognize how many holes there are, for example? These kind of questions, where it's like you need to know the whole surface and answer to give an answer to that question. And like the preparation that I want to do, like in the remaining time for today, is talk about the simplest version would be that you say like what is the total area of the surface. So that's like something that is like a global data where you need to have like small, like in a small patch you can like know the area, and then you have to patch all of these informations together to get like the total area. So another way to say that is that you like are interested in certain things that are integrals over the whole surface. So, and the way that we do that is by first getting some intuition by looking at local coordinates, and then trying to extrapolate from that. So, we have some local parameterization S, and as usually we have points which denote x and y in our region. And the question would be, what is now the area? Let's see, what is the area of the area of the image side? And the idea here is that E is something relatively nice in R2, and that becomes then quite deformed on our surface. And the idea is that on D, we kind of know how to calculate the area, because that's quite nice. So what we would do is just take like small rectangulars, and then divide your area in small rectangulars. And then in order to calculate the area of D, what you do is you measure the size of the small rectangular, and then you measure essentially how many of these small rectangulars fits into D. So that gives you the area of D. But we are not really interested in the area of D, but like what happens to the area if we consider it as something in the curved space. So in that case, we get like very deformed, like rectangulars. And you can like just transport everything. So the idea is to connect the area of like these small rectangulars on that side here that measure the size of these small rectangles and then sum them up. That's the idea. Area P is simple. Decompose. Sum them up. But each of these rectangular, there, in D gets deformed. On the chart. So let's see what happens like infinitesimally if you have like a very small rectangular. There you go a little bit to the point here, call that point x and y, and then you have a vector here that spans the rectangle. So that's in this case it would be v1 and 0, and over 1 in this direction would be v2 and 0. And then you get like corresponding vectors here. So in this direction. And we already know how these vectors over there, namely they're like the tangent map applied to phi. Vector v1, 0, 2. You think that tangent vectors in R2. Line segment. Side x and y to side x where we go now a little bit in the v direction. Linearly approximated by the tangent map. In the picture, with here one of the edge points, the side of x and y, and then here this other point would be x plus v1 point. And the blue arrow from here, y, at the point x and y in the direction of v1 and 0. So in an approximation, at least if you think of at least v1 is relatively small, but you can say if you go to this point, you approximately have to go in this tangent vector that is given by this linear. The linear approximation of that line is given by this tangent vector. And similarly, of course, we can do that like in the y direction. segment x and y to y plus 2 to approximate the and so if you now look at the area of the small rectangular that is given by R, that's transferred to the small rectangular of phi of R. So this area of phi of R is approximated by the cross product of these two vectors. Area of the parallelogram. For these two vectors. And we all know how the area of a parallelogram can be calculated, namely get an area of approximately as the same as taking the norm of the cross product vector. Okay, so we see that the area of like the small rectangular on the surface can be given in terms of these two vectors and taking the cross product and then the norm of them. And if you look at that, it looks very much like a Poisson operation. Right? You have like tangent map of psi acting on the first vector and the same tangent map acting on the second vector. So that looks like very much like the Poisson. So the idea would be to introduce a form of the true form. And usually you write the true form as like dA on S. You should think of that as a name. Satisfying to insert the true form. So we have to say what it is at two given vectors, the one and the two tangent vectors at the point of the surface. And if that's just product of one to two points, then we can write the area of the small rectangular is approximately the same as the pullback of this form it's a form then on D, and then this two form is then evaluated on here. So that's just like writing this formula up here, that the area of this one is given as the cross product of these two vectors. And if you have like a two form that will satisfy this equation, then you can just write the full work. Apply to two vectors. Because so this one is just by definition dA minus y, and then we have to put the root. And then we use this property so that it's really the same formula as we have upstairs. And the reason why we write it in a little bit of a strange way like this is the following, namely that we have and we get area of area of the whole, like the image of the parameterization would be a little bit formally written as like the sum over all the rectangulars and then the area of side of R. That's a little bit formal. So that means at least if you make the small, so it would be same as the sum over all areas, and then we would like to take this A there. So kind of like this. And sum, of course, just doesn't make really sense, but you make them like the rectangular smaller and smaller. So what happens is then that this one is actually the area would be becoming an integral over here over all of these pullbacks. And then the sum is actually more properly written as the integral. And so we get here over dA. And that's nice because then we can use the formula that we had for the integral of the pullback as integral over image of the over Thanks a lot, this was really nice timing. So now we found that the area of this parameterized surface is the integral over that area over a certain two form, and this two form has the property that it satisfies this equation. So it would be natural to define just dA by this formula over there. Area element. the formula that we had, namely that A at a point P, P1 and P2 just be the area of the parallelogram of these two vectors. And then we can just integrate over the whole surface. S to get the area, the total area of that. But there's a small problem, namely that in order to integrate, we need like an orientation. And if you have like the wrong orientation, then you might get like a negative volume or a negative area of your surface. And that's very confusing because normally you would say like the area of the sphere, for example, is 4 pi. But you don't want like to say like that it's minus 4 pi. So it's you really need like you need to choose orientation in some way compatible so that the result that you get is always positive. So we need to kind of incorporate the normal in the definition of dA. In a way that like if you change the normal to minus the normal, so you change the orientation by a minus sign, then also your dA should like switch by a minus sign so that the result stays positive. And think a little bit about that, and then you quickly come up with the idea that you just take the inner product with the normal. That gives you the following definition of the area element. Surface oriented. We're choosing a normal unit with normal